In this video, we're looking at how to find the least common multiple, or the LCM. It's important to know that the least common multiple is something that we can find among two or more numbers. You really can't find an LCM of just one number. An example might be, what is the LCM of 6 and 8? Well, let's break this down by what does it mean least common multiple? Let's take these numbers 6 and 8 and just write out some multiples. Let's start with the multiples of 6. This list of multiples comes from a couple of different ways. You could think of finding multiples of 6 by doing 6 times 1, 6 times 2, 6 times 3, 6 times 4, and so on. Or you could say, I'm going to count by sixes, starting with 6 and then add 6 over and over again. Add 6, add 6. So there are a couple of ways we can find multiples. That's just the beginning, the first 6 multiples. This list will go on forever. Multiples of 8, let's make up the list in the same way. There's 8 times 1, 8 times 2, and so on. So here are some multiples of 6 and multiples of 8. A common multiple would be some number that we see on both lists. And you're maybe spotting already that we have a 24 on both lists. So 24 is a common multiple. It's on both lists. It's common to both lists. And it's also the least common multiple. There are no numbers less than 24 that we find on both of these lists. So here's one way that we can see how to find a least common multiple. I want to take this opportunity to do a quick example of what's really the significance of a least common multiple. And the example I like is this example right here. If you've gone to the store to buy hot dogs, and maybe your brand comes in 6 hot dogs per pack, and the buns come 8 per pack. And the question is, how many hot dogs do I need to buy so that I don't have any buns left over and I won't have any hot dogs left over? Now remember, we just found LCM of 6 and 8 and got this answer 24, and it turns out that that is how many hot dogs and hot dog buns we can get without having any leftovers. If we were to get 4 of these 6-packs and 3 of the 8-packs, that's going to leave us with exactly 24 hot dogs and 24 hot dog buns. So it's a way that we can take two different numbers and see how can we build these two different numbers up so that they equal the same thing. Now, how we build them up is usually going to be different. It took 4 packs of hot dogs but only 3 packs of buns, but eventually we were able to get both of these numbers, 6 and 8, to this point where they equaled each other, and that's the LCM. We would be able to find another point where we could get these two to equal each other at 48 or 72, 96. Those are more common multiples, but 24 is our least, the lowest number that we can find. Now the way that we've just found the LCM for 6 and 8 by listing multiples is certainly a way that will always work, but it does have some drawbacks. It can be a pretty long and difficult process if we have numbers that are large, or if we have maybe 3 or 4 different numbers that we have to find the LCM for all of them. Plus, it's a way that does not work so well once we get into some trickier problems that involve a lot more variables. So we have a different way of working that at first it might seem like a little bit more work, but it is a way that is much more useful in the long run. So that's the way that I like to focus, and it's using prime factors. So we'll go back to this example of 6 and 8 because we know LCM of these two numbers is 24, but we'll look at a different process using the prime factors. The first thing I want to do is for each of these numbers, find prime factors, and I'll use a factor tree where I start with this number 6 and think about what two numbers multiplied together would equal 6. And when we're making these trees, we avoid using the number 1. So I wouldn't want to choose 1 times 6. I'll have to choose 2 times 3 instead. Now think about, can I do the same thing with the number 2? Can I say 2, I can get a 2 by doing this times that. And remember, we're not allowed to use 1 in the factor tree because 1 is not really a prime number. We have to stick to prime factors. So the 2, we can't break that up any further. We'll just put a circle around that and say that's a prime number. And 3 is also a prime number. And you might have some prior knowledge or just have good memory of this list of prime numbers, especially the smaller ones. But our thoughts are A prime number is something that the only way we can break it up into its factors would be using that number itself and 1. So 2, I can only do that by doing 1 times 2, so it's prime. 3, I can only break that down as 1 times 3, so that's prime. Okay, let's move over to this 8, and we'll do a factor tree. I'll come up with 2 times 4, and 2 is a prime. 4, we can break that down further and into 2 times 2, and those we've already decided are primes. So the prime factors of 6, 2, and 3. The prime factors of 8, 2 and 2 and 2. 3 2's. Now that we have the prime factors, we're going to build our LCM. Now this part right here might seem silly, but it's something that's helpful for me to remember what I need to do to find an LCM. Now first of all, the L helps me to remember that all the factors I see I'm going to have to use. I see some 2's, I see some 3's, they'll all have to be used. I know L all to stretch. And now there's a catch, because I don't want to just look at this and say, I see 4 2's, I want to use 4. That's really not how LCM works, and we don't usually want to think about finding totals. What I want to think about is, where do I see the most? That's the CM. This is silly, I know, but it might be helpful, and that's the only reason I'm saying it. So we have to use all these different factors, but we only want to use them where we see the most, and I'll explain what I mean by that. First, think about using a 2. How many 2's do we need in the LCM? Well, we want to keep these two trees separate so we can see in this tree there's only 1 2. In this tree we have 3 2's. So think about, in which tree do we see the most 2's? And I'd say it's over here on this side. It has 3 2's. That tells us that we need 3 2's in the LCM. And we'll go over a few examples to get these ideas working for you, but it's about, in which tree do we see the most? That's how many factors we have to use in the LCM. Okay, now you're thinking, we have to use them all, so we have to think about 3's. Where do we see the most 3's? In this tree we have 1 3. In this tree there are no 3's, so definitely over here is where we see the most, where we see 1 3, and that's how many we'll need in the LCM, 1 3. And there are no other prime factors. Don't look at that 4, because we're thinking prime factors only with this method. So I'm only interested in these numbers that are circled, like the dead ends of the tree. 2's we covered, 3 we covered, no other prime factors. So we finished building the LCM. The last thing we can choose to do is to multiply all these numbers together. 2 times 2, 4. 4 times that, 2, 8. And then 8 times 3, 24. Just giving us that answer that we expected to see, but we're seeing how we can get there in a different way using prime factors. Let's move right into our next example. Find the LCM of 36 and 56. So we begin with finding our prime factors. And I'm always going to use this tree. With 36, I think this time I'll choose to start with a 2. So 2 times 18, and 2's prime factor. 18, we can break that up further. Going with 2 times 9, 2's a prime factor, and 9 we can break that up 3 times 3, and those are both prime factors. Now, a quick reminder about these factor trees, it doesn't matter what sort of multiplications you choose. So if you're choosing 6 times 6, that's okay. Just remember that everything must be broken down until we get to all the prime factors. And if you do that, we're always going to end up with 2, 2, 3, 3 if we're breaking down 36. Let's go and break down 56. This is another even. It's 2 times 28. We'll circle that 2, the prime. 28 is 2 times 14. We've got the prime is the 2. 14 is 2 times 7, and both of those are primes. So we found prime factors of 56, 2, 2, 2, 7. Prime factors of 36, 2, 2, 3, 3. Now let's build the LCM. Okay, we have to use them all. So 2's and 3's and 7's all must be seen in our LCM. But where do we see the most? Where do we see the most 2's? On this side we have 2 2's. This side we have 3 2's. So here's where we see the most. 3 2's is what we'll use in the LCM. Next, 3's. Here we have 2 3s and none on this side. So in this tree is where we see the most 3s. We see 2 of them, so we will use 2 of them in the LCM. And lastly, the 7. So we have 1 7 over here. No 7s showed up out of this tree for 36, so we're using 1 7. And finally, let's multiply all these factors together. This is a big one, 504. Multiplying 2 times 2 times 2 times 3 times 3 times 7. And 504 is our LCM of 36 and 56. That would be a lot of hot dogs. If hot dogs came in packs of 36 and buns 56, that's a lot of hot dogs. Now let's look at an example where we're finding an LCM of 3 numbers. Our approach really will not change. We will begin with finding the prime factors. We will this time have 3 trees, one for each of these 3 numbers. So let's start with 16. This time I think I see 16 as 4 times 4, but I'm not stopping there. 4 we can break down as 2 times 2, both prime, and that 4, same thing, 2 2's. So we have 2 times 2 times 2 times 2 would equal 16. Next, 18. 2 times 9, and there's our prime, and 9 is 3 times 3, so we have 2 more primes there, 2 times 3 times 3. And finally, 20 is 2 times 10, there's the prime. 10 is 2 times 5, and those are both primes. So we have prime factors in 3 different trees. Our rules about building the LCM are still the same. We'll have to use all these different factors, 2's and 3's and 5's, and we have to choose them based on where we see the most. So let's start with 2's. Where do we see the most 2's? Okay, definitely in this first tree, we have 4 2's. Now, you can make a choice sometimes about how we write out these prime factors. Instead of writing 2 times 2 times 2 times 2, I'll use some exponential notation. 2 to the power of 4. And we should know that here's our base 2, and this exponent 4 tells us how many times we would see the number 2 in a multiplication. So 2 to the 4th power is exactly our 4 2's. Next, 3's. Where do we see the most 3's? Well, none there, none there. Here we have 2 3's, and none here. So here's where we see the most. We will be using 2 3's. And just to keep using exponential notation, I have 3 to the 2nd power. 5's, none, none. Here's 1 5. So we will need to use 1 5. And if it's just 1, it's okay to write that without an exponent of 1. And if you had an exponent of 1, I think that's okay too, but not really necessary with just 1 5. Let's multiply these all together and come up with our numerical result. I'll do these exponents first. So 2 to the 4th is 16. Well, we should know that. There it is. 2 times 2 times 2 times 2 is 16. 3 to the 2nd power is 9. And we have that times 1 5. So there's 144 times 5, 720. Okay, so the LCM of 16, 18, and 20 is 720.